So lazy evaluation and lazy data structures achieve a certain style of programming that allows you to increase modularity in programs. Lazy programming style makes a clear separation between where the computation of a value is defined, for example, a single function, and where the computation of a value happens. So there's no longer a clear link between the order in which definitions are made and the order in which computation is made. In that sense, computation in some sense kind of hops around between different definitions when you have a lazy evaluation. Now, lazy evaluation was one of the core design goals of the Haskell programming language, to build a programming language supporting lazy evaluation. It wasn't the first programming language of this style, but it was certainly one of the central features that was intended. Once you decide that you're going to have lazy evaluation, then the choice of having purity, having side effect free functions, kind of follows along very naturally. And the reason for that is because it's very hard to predict when certain computations will take place because of the lazy evaluation. So side effects really don't work well when you can't predict when they're going to happen. And so in some ways, lazy evaluation is responsible for much of the important parts of the design of the Haskell programming language, such as the encapsulation of side effects through I/O and the I/O monad. And in many ways, although lazy evaluation is responsible for many of these features, lazy evaluation itself, in retrospect, is maybe not the most important aspect of Haskell. But maybe the way that side effects are treated and controlled turns out to be a more important feature of the Haskell programming language, even though it was really just a consequence of having to work with lazy evaluation. So if you recall the Sudoku lab, for those of you that have started the Sudoku lab, lazy evaluation plays a central role there, and it's not in a way that requires you to think very much about how it works. But the idea will be that you will implement a notion of backtracking, a search algorithm, but without having to think about search at all, thanks to lazy evaluation. And the way this works is you write down an expression which represents all the valid solutions to a Sudoku puzzle, and you simply pick the first one. And by doing this, you will notice you'll be able to solve a completely blank Sudoku in a fraction of a second. But if you actually had to compute all the valid solutions, then of course you would never be able to do that, because there are way too many valid solutions to a completely blank Sudoku. But because you only need the first one, then you can compute these very quickly. And in fact, the lazy evaluation then in this style will actually implement the backtracking for you. You will try to compose all the possible solutions, throwing away any bad ones as you go along, and just simply take the first good one that you find. And that will embody this notion of backtracking. It'll make more sense, of course, once you've seen the lab itself. Now, we've seen in the introduction, if you've looked at the video that was linked, the intro video that linked dealing with infinite lists, that we can work with infinite lists in nice ways. And that those examples, I think, led to, for example, the definition of the classic primes sieve of Eratosthenes, where you build the infinite list of prime numbers, and you do so using a classical algorithm which renders to basically 2 lines of Haskell code. So we can compute the primes, and the primes, well, we can't compute all of them, of course, but we can stream them to the output, and we can inspect as many as we want. And an example of how this leads to a very modular programming style is we have one definition of primes, and we can use it to define a whole bunch of things. For example, the first n primes will be just computed by taking, for example, the first 100 of the primes. We can compute the first 100 primes. Or we can compute all of the primes below a certain number let's have another example, the primes below example. We can take all the primes below a given target value, the primes below 1,000. Right, what are all the prime numbers below 1,000? There they are. Another example, the primes in a given range. Well, let's just take the primes below the upper bound, and throw away the ones which are below the lower bound. So that would be all the primes in a given range. And finally, the one that's given in that video that was linked were the twin primes. Twin primes are pairs of primes which are only 2 apart. You can't get any closer than that except for 1 and 2, of course. The first two primes are only one apart, but all the others are at least two apart. And so how do we compute them? Well, we take the primes and we take the tail of the primes and we zip them together. So then we get the first prime and the second prime. Well, let me just try the zip trick. If we take zip of 1 to 10 and, for example, 2 to 10, so we've taken a list and the tail of that list and we've zipped them together. Then we get 1, 2, 2, 3, 3, 4, 4, 5. So we get all pairs. So we do the same trick here. We're zipping a thing with the tail of that thing and we get all pairs, consecutive pairs from that list. And then we filter out all the twins from those. And a pair of numbers are twins if the second number is the first number plus 2. So the twin primes, we can compute the twin primes in that way, and we can see we get plenty of them. Now, how many do we get? Well, of course, it's a classic conjecture, the twin primes conjecture, whether there are infinitely many or not. So if we let this, if we keep this going, it may print out, may keep printing these out forever, but it may not. And if it at any point seems to stop, we won't actually know whether it's stopped or we just have to wait a long time for the next one. Okay, so these are good illustrations of using infinite lists, for example, to achieve a modular programming style. One other little detail about this example, you notice that we're using primes twice here. And you may be concerned that you're computing primes twice, once here and once again to compute the tail. But since this is a single definition, then this will be shared. So this will be one of these examples of a shared computation, so that any computation we do for this one will be reused for this one and vice versa. So there won't be any duplication of the computation of the list of primes, however many we happen to print out. We'll only compute each one of them once. So the Haskell prelude contains a bunch of functions which only make sense because we can work with infinite lists. And although they might be not very useful on their own, they can be useful building blocks for many programs. For example, iterate takes a function and a starting value and iterates the function over that list. For example, it returns the value followed by the function applied to the value, followed by the function applied to the value applied to the function applied to the function applied to the value, and so on. So an example here, we iterate the times 2 function starting from 1, we get the infinite sequence 1, 2, 4, 8, 16, and so on. So you could use something like this to compute some kind of numerical analysis algorithm, computing the convergence. You can stop when the distance between any two is below a certain delta, for example. An even simpler function is one which just simply repeats an argument infinitely. And a third example is the cycle function, which takes a list, which typically will be finite, and generates an infinite list by repeating the finite list over and over again. So all of these may appear to be not terribly useful, but in fact, as building blocks for other programs, they often turn out to be quite handy to use.